when do we get maximum transfer of power from a source to a load? You should have done that in circuits and in 322.
When the load impedance is the conjugate of the...
Exactly. That is exactly true. So practically, when you have a load, and then a source here, V, and let's assume that this is the source impedance. And then you have a load here. To have a maximum, the condition for maximum transfer of power from the internal source, to the impedance from the source to the load is if the load is the complex conjugate of the source impedance. Okay, I'm not going to prove it. There are a lot of proofs in different books that you have already used for your classes, but this is just to remember. Now, let's assume that we want to design a circuit. We have an impedance. We have a source. And I will take this and modify it. So let me do this for a second. And then I will put a load here. And this load, obviously, the way we have it is not the complex conjugate of the source. So let me give the load here. Let's assume that this is, that Vs is 1 volt. Let's assume that Zs is 50 ohms. And or maybe let's do it a little more complicated. Cs is 100 plus J50, right? Then we have a load, which is what do we want to make the load? Let's make the load 100 ohms, no, 50 ohms, or 80 ohms. And now the question is, what are we going to put in between to be able to get the maximum transfer from the source of power from the source to the load? Okay, so let's assume now that we are going to put something in between. And what we're going to put in between, we're going to call it the matching network. All right, so it's called the matching network primarily because it matches the load to the source. And it's complex conjugate matching. All right, so let's assume that this is the input port is A prime, the output port is B prime. And all right, so the question is, now that we know what we have to do, how we will go about it. First of all, we know that if these from the matching conditions, so let me write it here also what the problem is before, because I'm going to have to publish the slides. So find our design, the matching network. so that we have maximum transfer of power to the load. Okay. Now the load, it does not have to be a resistor. The load could be an antenna. So practically, if I have a source with an internal impedance, that source can be an amplifier. And I want to connect it, this power amplifier, to the antenna. Then I want to make sure that I put something in between, so the maximum power from the amplifier goes into my antenna, and then it's radiated from there. So, but this is the most simplistic representation of this problem. Okay, now let's assume that this is the input impedance at AA prime. All right, so Z input at AA prime. So we know, so the solution is here, solution. So we know that we need to have the following condition. Z sub S should be Z sub in at AA prime at AA prime complex conjugate, or this one. All right, so we know, therefore, from this, from 1, we find that Z input at AA prime has to be equal to 100 minus J50. All right, so we know how much this impedance should be. Okay, now let's see what we have to do. We have to take this impedance here and transfer it with whatever we are going to place, and then now we have to think what we're going to place. But we have to transfer this impedance to ZL. We have practically to go from Z input, so the matching network, that's how we call it, we saw it, transfers Z in, which is 100 minus J50, to ZL, which is 80 ohms. Or in other words, you also have to say, in fact, I can represent that in a different way. And or depends on what I find easier to understand. Let me, in fact, do this here for a second. Or VMN has to transfer ZL, which is 80 ohms, to Z in, which is 100 minus J50. Okay, how do we do that? Let's think of the problems that we did for the previous homework. All right, in the previous homework, what we had is the following. So from previous homework, we had the following. We had a transmission line, and in that particular case was a quarter of a wavelength, in one case half a wavelength in another, but we had a transmission line, and then I will put the length at the end to see how we're thinking about it. So it was a transmission line here, It has a length L and a characteristic impedance Z01. Then we had the load here. We had ZL. Or RL, say you like it. And then here we had a shunt stub. And also here. All right, so that was the stub. And the stub could be open or short. So open or short. And the stub can have a different characteristic impedance. All right, too. That's what we did in the previous problem. And then in the previous problem, we knew what was the input admittance or impedance, because if you know the admittance, you know the impedance. And then we found the length of the stub, D, and we found Z01. So practically we had to find, I just remind you of what we solved in the previous homework, Z01 and D. And D. So what are the things that we observed in this one? Let me write here the observations. Observations. I'll start with the simplest one. A series or a shunt stub. This is a shunt stub in parallel. So a series or parallel stub shunt stub can only add a reactive load. What that means, that if I look inside the stub from here, let's assume that this is A prime, B prime. All right. So what that means is that if I look here to find the input impedance inside the stub from AA prime, and let's assume that I call that Z input. All right, Z stub if you like, or Z input at, I will call it Z stub rather, Z stub at AA prime. Right, so let me call that input impedance, or I can think of it the inverse of that, which gives me the admittance. Oops, excuse me. This is 1 over YS at A prime. Okay. Either ZS or YS can only be reactive. Why? Because if the stub, so let me write here. So there are two cases. A, if stub is open, then Z sub S at A prime is equal to minus J Z02 cotangent of beta D. All right, and or YS at A prime is 1 over Z02 J tangent beta D. All right, so if the stub is short, at the end, then z sub s at a prime will be equal to j z02 tangent of beta d, or ys at a prime will be minus j 1 over z02 cotangent of beta d. In both cases, what we find out is that the load of the stub is always reactive, is always imaginary. So then the load of the stub, we write it here, okay. So observation number 1. Observation number 2. Let me put them here. You don't have to write these observations in your solution. I just write them to help you practically. So observation number 2 is observation 2. If the stub is a shunt stub or a parallel, so if the stub is a shunt, which means connected in parallel, then I need to work, we should work with admittances. Why is that? Because when we have parallel combination, the admittances add up, all right? So shunt admittances. 2. If the stub is series, meaning connected in series, then we should work, rather, I should say here, work with. Then we should work with impedances. These are things we need to remember. All right. So far, it's just nothing new. All right. So let's see here what we have to do. We have to change, to go from a load, which is 80 ohms, 80, to an input impedance, which is 100 minus J50. So first of all, we need, you have a real load transferred along a line. The first thing that I would do is to remove, I will have at some point to remove its reactance, or to add reactance in this particular case, all right? Remove reactance when I go here, add reactance when I go like that. So since I move from the load towards, I go like this, as I'm thinking about this design, I'm going this direction. So my R sub L, now it's real. It will have to go through this line. depends on how long the length of the line is and how long its characteristic impedance is. It will have to change, and it's going to be either real or it's going to become complex. Now, I want to keep things simple. So I would say, what if, as I move from BB prime to AA prime, I use the line here to keep my impedance in the beginning of the line, to keep it real. But in addition to that, I will have to make it, the real part of this impedance, 100 ohms. And then I can add the stub to remove whatever imaginary, well, and then I add the stub to bring the imaginary part to minus J50. So practically, what I'm saying then is what I'm thinking, all right? So conclusion on the basis of that. Conclusion is the following. And that's one possibility. There is not only one way of doing a design. There are multiple design opportunities. So there are multiple designs that can work also. But this is one, all right, based on what we did in the previous homework. You don't have to follow it, but I'm just giving you, that's the thing about design, as you know, many of you, that there are multiple solutions. There's not only one. So in any case, the conclusion is, so one possibility, okay, design number one is to, let me take this again. So copy and paste. Okay, what I will do now to simplify some things, I will remove this. All right, and then I will say the following. Design number one, and I will write it in green. I design, oops. The line Z01, and let me call that Z input at A prime, so that Z input at A prime remains real. Okay. All right, if it remains real, then, well, and then let me continue. This is just outline of the design. So first, I designed the line Z01, so Z input at AA prime remains real. And then 2, after that, remains not only real, but also equal to 100 ohms. Let me do this. Remember, these are ohms. Okay. Remains real and is equal to 100 ohms. And then second step, I design a shunt or a series stub. All right, since I work with impedances here, I can design a series stub, or let me put it shunt. I design a shunt stub so that, well, in fact, since I'm using impedances, I will follow my previous observation. I will design a series stub that has ZS at A, whatever we call it, at A prime to be equal, and I will change the position of the stub since it's a series, to be equal to minus J 50 ohms. So practically, in this case, I have to remove this from being a shunt, as I said previously. I will make it a series stub. So here, see how I'm gonna do that. I'll move this a little further out. There. Then I will here. This is A. And then here I will have A prime. And then here in series. Oops. I'll use a series stub. And I can expect this to be open or short, depending on how we are going to decide to do this. Let's assume that it's short in this case for a moment. You can choose it because, you know, nobody is asking you, they just want you to do it. They don't give you any more constraints. All right. In fact, you can say, I can assume that this is going to also be. I said that assume that Z naught is going to be 50 ohms. It will have 50 ohm line sections. Interesting. So this one is going to have Z0. All right. And then Z0 here. Let's see whether there is one constraint, because the constraint here, the one that the problem has, is that the lines have to have a characteristic impedance of Z naught in this problem. Okay, so now let's see what we are going to do, how we are going to manage that. And Z naught is 50. And then this one, what did I give? Let me see if I get in the problem I gave that. In this one, okay. In this problem, I'm giving you what I said, Z01. I don't put any constraints at this moment. All right, so I do that. I have two things to do. Design the line Z01 so that the Z input at AA prime, which is this one, remains real 100 ohms. All right, remains real, but becomes 100 ohms. And I design a series stub that has a ZS. Let me, in fact, well, okay. This is an A prime. Let me call that A double prime, because it's different than A, obviously. This is A. All right, so A double prime here. All right, so the stub has to be designed. We have to find D. So that it gives minus J50. All right, from the first one.
Excuse me, Professor.
Hello?
Hello?
There is no, okay, there is no in the system. Then we have learned, so now I'm trying to do the things that I've learned. What do we know? We know what? That a quarter wavelength transformer can transform real to real. All right, so we know that in a quarter wavelength transformer, which in fact is something like this. That's lambda over 4. That's a load, which is real. And that's an input impedance, which is also real. And this is Z naught. We know that Z naught squared will be equal to RL times Z in, which implies that Z in, the input impedance, the real input impedance, is going to be Z naught squared divided by RL. All right, that's what happens in quarter wavelength transformer. So now let's see how we are going to apply it here. I put Z01 here. We know that RL is 80 ohms. We know that Z in, it has to become 100 ohms. And therefore, from here we find that Z input at A prime is going to be equal to Z01 squared divided by 80, and that has to be 100. Up from here, we find Z01. It's going to be the square root of 8,000. And this, let me see, 1, 2, 3, square root. This gives 90 ohms, gives 89.45, which I will assume is close to 90 ohms. Okay, so we found Z01 is 90 ohms, and then its length will be lambda over 4. So this kind of thought led us to this design of the section of the line. All right, now we will have after that to design the stub. But we found so far Z01 and we found the length of this line. All right. Number 2, so now we go to design the stub. If now we have Z01, and I put what we found here to be 90, and L is lambda over 4, Z input and AA prime is 100 ohms. So practically now I need this impedance here, and then I can use it I can use a different color here. This impedance here, which I call A double prime A prime, I need that to be minus J50. Now this I will do with the Smith chart, all right, because that's the easiest way to find it. Let me therefore do this, make that a little smaller. Okay, and that a little smaller. Okay, and then I will have to find the Smith chart. 1 second. Okay, copy. Paste. Okay. there, perfect, goes there, so we can move it a little higher up and then clean it up. Okay, so now we have to develop a stub that has here an input to the stub of minus J50. To do things on the Smith chart, okay, to design on the Smith chart, we have to normalize impedances. To design on the Smith chart, we have to normalize. All impedances. Okay, and we're going to normalize with respect to Z01, because that's the common characteristic impedance, which is 90 ohms. Okay, so we have to normalize ZS, the A double prime A, which means, so now we do ZS A double prime A prime normalized is ZS A double prime A prime divided by Z01, and that is minus J50 divided by 90. 50 divided by 90, and that becomes a number then, as before it had units. Okay. Let me see. Is 50 divided by 90 equals, and that is minus J.55. All right, now we go to find that point ZS normalized of A double prime A. So we are going here, we are looking on the Smith chart, where is minus 0.55, and then all of the minus are in the lower part of the Smith chart. And then 0.55 is here, minus lower part. And then that is ZS A double prime A prime. So this one, it does not have a real part, obviously, it's only imaginary. And this one here is ZS A double prime A prime. Okay, now we want to make that, we want to go there, we want to have that with the stub, and we have decided to make the stub what? Short-circuited. Where is a short-circuited stub? The load of a short circuit is 0. So the load of the stub is going to be here. All right. And then we will have to, if the load of the stub is here, we will have to move along a circle that goes through this point and has the center of the Smith chart. And this circle is going to be this one, the inner circle of the Smith chart. Oops. Do it quickly and I will fix it. All right, so okay. Now we will have to move from the end of the stub, which is short. So from the end of the stub, which is short, which is here, I will use a red color. I will have to move from that, and that's the end of the stub. End of stub. And we have to move towards the generator, so we are moving this way. But we have to move until we come down here. So we're gonna move like this. All that circle. Okay, we'll go all the way until I stop here. And now I need to find out what kind of a length in this stub I should have. To find the length of the stub, I will have to write this line here and this line here. And then to see how far I went as I moved around like this. All right, I moved around like that until I came here. Now I move from position of 0, I go around, I arrive here, which is 0.25 of a wavelength distance, and then I come, I continue until I measure here, and I see it's 0.418. So the distance, the length of the stub, D, has to be 0.418 wavelengths to be able to do that. Now, the interesting thing is that if the stub, that's for a shorted stub. Let me ask you this, if the stub was, let me see, if the stub was to be open, where would I start? Where would the end of the stub be if it were to be an open stub?
0.25.
It
The
would,
exact opposite
yes,
end, 180.
Exactly. It would have been here. All right. And I would have to go around this distance, which is much shorter than the other one. Sometimes having a very long stub is not a good idea. Why is that? Because a long stub of a microstrip, especially if it goes close to a wavelength, is going to start radiating like a small antenna. And so even if you're not going to have losses, having a stub which is close to 0.5, all right, you're going to lose a lot in radiation, and radiation is going to also create crosstalk coupling to other microstrip sections. So what you observe from here is, so I'm going to write it as observation. So observation is the following. Okay. A short-circuited stub is too long. To be incorporated in a real design, in a real circuit. So as a result, it is better to use an open circuited stub. To use an open circuited stub. Okay, and in this case, what we would have is that D for the stub, it would have been, if we remove from 0.418, it was not 0.418. If we remove 0.25, it's going to be 0.418. 0.418 minus 0.25. 0.418 minus what? It's 0.168 lambda, which is very reasonable. That's how you would solve this problem. Now, there are other ways. Any questions so far?
Yes, excuse
Yeah.
me, Professor. Do
Yes.
you mind if I ask why did you choose the length to be a quarter wavelength?
Because
And-
that's the only time a section of a line transfers a real load to another real.
Okay, so if the load is not real,
Then I would not do that. I would do something different if I have to choose. All right.
right?
Yeah.
Okay, so if the load is not real, is there a certain length that we should
No, well,
consider too?
there are other ways of solving the problem, and I will show it to you on this problem.
Okay.
Without
you.
changing, designs have multiple ways of solving a problem, all right? There's not only
Right.
one solution. Okay,
Right.
so now
Thank
that we have done this, let me see. Let me ask for any other open or short and show you another design. So that was design number one, you remember? Design number one. Any other questions before I continue? All right, let's now take the same thing. I'll take the initial. Copy. Okay. Paste. And then call that design number two. Each one of them is a possible design, all right, for this problem. Because I have not given you restrictions. If I give you restrictions in your design, then some of the solutions will not be possible that now are. Okay. Now I don't want to do what I did before, but let's say, what if, I assume right now, what if, all right, if I make Z01 to be equal to Z02 to be 50 ohms. Okay, that's my choice. Then what I will go to the Smith chart, obviously, because now I made both of these characteristic impedances the same, and I can solve the problem using the Smith chart, because I will show you how this is something, at least for my class, we did it in 322, but I will remind you for those who had done this before. First of all, since we have in this approach the same characteristic impedance, now I will normalize everything that I know in terms of impedances with respect to 50 ohms. All right, so after I made that decision, I normalize now. Both R sub L and Z in with respect to 50 ohms. What does that give me? R sub L is going to be 80 over 50. Is going to be 1.6. And Z in, let me do this here. Right. And Z in is going to be 100 normalized. 100 minus J50 divided by 50, which makes it 2 minus J1. Okay. Now I'm going to the Smith chart. So now I'm going to take this Smith chart, copy it. Oops. There, thank God, I thought I copy. There. Okay. Let me in fact make that a little smaller. So let's J1. Move this a little further up. Begin. And now I'm gonna clean it also. Okay, and now I'm gonna place on the Smith chart RL and then Z input. For RL, it's 1.6, it has only a real part. So practically I have to find it on the horizontal axis and it's 1.6. And then I'm looking where is 1.6, which is here. 1.6. And this one is R sub L normalized. So I'll put it here, R sub L normalized. Then I'll put Z in. Z in has a real part of 2. So I will have to write the circle that goes through 2. Okay. And then his imaginary part minus J, I'll do it with gray, with green, is this one, the circle. And therefore, this is here. Okay, wants me to do it there. All right, so this one now is Z in. Okay. Okay. I wanna move on. I wanna find a section of line. All right, that is gonna move RL to a point, and then from there, I hope that I can to see where I'm going. All right, practically, I have to go from let me change the colors of just to, I have to go from this to that. Okay, I have to go from this to this impedance. And there are only a few ways I can do it. All right, so I can only, if I move along a transmission line, say if I keep this line here and I go along this transmission line from the load to the generator, the only way I can move around it is through a line which goes through the center of the chart. Let me do it with blue. Through the center of the chart, the center is the center of the chart and goes through that point, Arsabel. So practically, the only way I can move from Arsabel on a transmission line is going around a circle like this. That's the only way of doing it. There. Oops. Let me try it again. Okay. Okay, there. I cannot go anywhere else, but I can only go around this. And as a matter of fact, I can go around only in this direction because I'm at the end of the line and I'm going towards the generator. And that here it says towards the generator. And but if I keep going on this line, I will never reach this point here. All right, this is the point where I want to be. I will never be able to reach this point. So obviously I need to be able to add a reactance. If I want to add a reactance in the line at the end of it that you see here, then the only way I can move from any point on this circle, let's assume that I moved from this red point and I arrived here. Let me assume, all right, that I arrived, I could be at any other point, but let's assume that I arrived at some point. Where do you want to stop? Let's assume that I stop here. Okay, I go there. Then from there, the only way I can go is either along these lines, because these are the reactive lines, either up or down. All right. If I move further on this, if I move further than that, I can only go up and down on the line along here. All right. And if I go back to the original, I've traveled so much, none of this arrives to my point. And if I travel so much that I arrive here, the only place that I can go from there is this one. That tells me that just by using a transmission line that has 50 ohms, which I selected, will never allow me to find a way to go from my initial point, which is this one, to my final point, which is this one. So my initial point, let me also do it red because that's where it started. All right, so if I want to go from Arsabel to Z input, I will never be able to do it for as long as my line is 50 ohms. So what is the way that I can overcome that? One way to overcome it is to say, okay, what if I don't make the line 50 ohms, but I make it something, so this circle that I have here, this circle, becomes bigger. If this circle becomes bigger, so now I will show you here. If this circle becomes bigger, like this, all right? Then practically there are points on the circle, and especially the ones that intersect with, so let me erase those for a moment. Let's assume that my circle becomes bigger, the circle that goes, of course, the point has to change, all right? But let's assume that I have a bigger circle, and it needs to interact with the red circle, because this way, if I were at a point like this, if I were at the point here on this circle, then I can move down along. If I were, let me see, then on this circle, that particular, not this point, oops, let me see. So this particular point, if my circle is the blue one now, this particular point here is one that can get me into the green point. Why is that? Because if I move along the red line, then practically from there, that implies that I'm adding a stub on the line. And when I move along the red line, because all of the real, and I'm adding a stub in series, because all of the real points of the red are the same. Therefore, the difference between the purple point and the green one is that they have the same real part, but they have a different imaginary part. And I can do that by adding a series stub. So what that tells me is that I have to normalize R sub L in a way that the circle that represents the transmission line is bigger and intersects with the red one. The way that that can happen is if I select, so to go to this circle, the big one, this one, let's assume that I like this circle here. All right, I selected it. As I said, there are infinite many possibilities in design for the problem that I have given. So to go into this, that implies that this point, the red one, has to change its position, and the red point has to move either here, all right? If the red point moves here or there, then practically the blue circle is the circle that this point can move around. How then my point moves there? So my normalized resistance is either should be there or should be here, one of these points. How can it get it there? By changing the characteristic impedance of the line. So for example, here I got 50 to normalize it. But if I wanted R sub L to go down to point, this one, in this case, let me also show you the values. In this case here, yeah, all right, in this case, the value R1 normalized is going to be 0.03, no, 0.32 rather, okay, normalized. And the one here that I show it, that is going to be 3.1. All right. Let's assume that this is solution one option one. And let's see which one we're going to select. Option one. And this is option two. Okay. When do I have option one? Option one, remember that R sub L is 80 ohms. To go to a normalized value, all right, so that's option That implies that for R sub L to be 0.32 normalized, it implies that 80 over Z01, which in the beginning I did not specify, should be 0.32, or Z01 should be 80 divided by 0.32, which in fact makes this impedance 80 divided by 0.32, 250 ohms. 250 ohms. Now, if I were if I don't care about doing it in microstrip, I would say, okay, this is one way of doing one characteristic impedance. But if I were to materialize that, I would find that it's going to be very hard on microstrip to realize this. So this is a very high impedance. So I'm telling you, this is the considerations that go to a different design. Theoretically, on paper, you can use it, obviously, and nobody's going to take it wrong. However, if you go to the lab to make a design, that's a very high impedance, very high to realize in microstrip. So what would you do? Okay, let's see. You would like to see what your other option is. Option 2 will be to go from RL, which is 80 ohms, to have an RL normalized, which is 3.1, which means that your Z0, Z01 has to be 80 divided by 3.1, which makes Z01 to be 80, sorry, 80 divided by 3.1, which is 26 ohms. That's better for a microstrip. So between the two, I would prefer the lower impedance. However, as I said, if I were to give you something like that without any constraints, without asking you to materialize it, you could use either one. But for microstrip, this is better. That's a better value. Eventually in class, we're going to see why. Better value. Okay. So now let's assume that I choose option 2. Option 2 is point here on the right-hand side, is this point. So now I am gonna make that blue to see which one I'm using. And from there, I would have to move around the around the circle now in that direction. And then I will have to move it until until I stop either at this point here or at that point there. All right, there are 2 points that intersect my circle with the red one where I have to go. And eventually it will go to the green point. So I can now again decide which one I'm gonna do. Am I gonna go down here, which is possible? All right, I can make my line to go there. Or am I going to down here? I'll tell you why I'm choosing the one up here. Say, call that A and call that B. So I'm choosing A because when I will try then to use a stub, I'm gonna have a reasonable line length to realize. You will see that when I'm developing it. So I go from my RL, option 2, that's the option I'm selecting. I will make it in blue. Blue, all right? And then from here, I can move along the line to the point A or point B. So I move along the line. To point B. And then from point B, what would I do? I will move along the constant resistance circle, which means I add in series a stub to go finally to this point, which is the green point is my destination. And how then do I find the length of the line and the stub? For the line, I will draw, let me see, for the line, I will draw here, this, from the beginning where I started, which is this one. And then where I ended, which is this one. And then I will go from here, move all around. I will move all around. All right, move all around until I come. Let me move a little bit this one up here. Just a second. What's the problem with this one? Jeez. Okay, I will move all around until I come to this point. All right, so I will move from there all around here, here, there, until I come to this point. And then that's gonna show me how much length I have to move around on the line. This is 0.25. This is 0.5. Therefore, I have to move by a quarter of a wavelength plus then whatever goes from here to there. And that is because it from after 0.5 goes back to 0. And that is 0.21. So practically it's going to be the length for the line is going to be 0.25 plus 0.21. Which makes the length of the line to be this much. It's okay to have a length of line this long. It's not okay to have a stub this long, all right? So this is gonna be the length of the line. If I had not moved to this point A, but I have moved to point B, the length of line I would move will be less than, will be so short, and then the stub even shorter, all right? Because for the stub right now, to find the length of the stub is, I will have to find, first of all, how much the value of the reactance is. Find the value of the reactance, I will have to go from A, to find the reactance of A. The reactance of A is here, and then which is in fact, this is the reactance here, is 1.5 positive. And then down here is minus J1. So I have to sum up this. If you remember, this is where I stopped on the line, all right? So I have moved now, this is a series stub, obviously, again. All right, so let me clean it up a little bit. In that case, I will do the same. I will have here series tab. Not very different from the previous solution. The only thing is that I did not use a quarter of a wavelength. And this is something you can do for any complex load, as a matter of fact. All right, so if your load is complex, you can do the same solution, since you asked me. So in this one here, I found that L will be equal to 0.46, I believe, lambda. And what I found is when I move from here to A, and I go to by 4.46 lambda, then A, the impedance that I will get at this point, this normalized impedance, and then let's call this A prime, let me call that B, for example, right? The impedance between A and A prime normalized, I can read it from the Smith chart. It's going to have a real part of 3.1. Let me see. No, it's not. I think there was a 1.2. That was 2. In fact, I'm so, you know, 3 was there. So that has a real part of 2. I mean, okay. What time is your class? Yes. So here is gonna be, let me write it down. That point. Okay, that point A. So Z input here, which is practically your Z input at A prime, will be 3. No, excuse me, 2. And then the reactive part is up here, plus J 1.5. All right. And then we want this to go to Z in, and we have found Z in normalized. Now we normalized with respect to the new Z01. We found, if you remember, that Z01, the same thing here, will be 26 ohms or something like that. How much did we find? It's gonna be. We move it either there or there. And what did we select? 01 to be 26 ohms. And if that is the case, the Z input is gonna be more than that. In any case, let's assume that I had let's keep going with this so we can finish it. But practically what you find is the input here is this, and then the point you want to go is 1 normalized 1 minus, well, not really, is point, it's 2 minus J1. Yes. So in this case, if I have these 2 minus J1 is 2 minus J1. And if I have this to be 2 plus J15, and I need to transfer it to 2 minus J, that means that this impedance here, all right, will have to be the impedance of the stub. We have to have the following normalized. We have to have the following relationship: 2 minus J equals ZS normalized plus 2 plus J 1.5. So this and this goes, and that tells us that ZS normalized has to be minus J 2.5. So more or less, I drew this to see that there is another way of doing it. There are multiple designs you can do in this problem because of the way I have given it. But the first design was the simplest, all right? And of course, it allowed me to do that because R sub L was a real number. Now, let me see any questions of this before I make a comment to what you're asked me. Just 1 second. Oh, sorry. 2, 4. Okay. The colleague asked me how we were gonna solve the second problem. In the second problem, let me give you some ideas. In the second problem, all right, so if we go away from this one, let me now make comments on the second problem. Specific comments about the second problem. All right, now the interesting thing about the easy thing about the second problem is that I have asked you already to use a particular characteristic impedance, which is Z naught is 50 ohms. So you don't have flexibility in selecting something else. Then in this case, if you normalize everything, your ZS becomes 1, and therefore your ZL at AA prime has to, or before you normalize, your ZL at AA prime for maximum transfer of power has to be what? 50 ohms because of conjugate matching. So your Z sub L at AA prime has to be 50 ohms for conjugate matching. And then you need to move. You need to normalize ZLBB prime, all right? And then try, if you normalize it, place it on the Smith chart and do a problem. So you normalize everything. Which is how much is going to be? 2 minus j 0.6. And then what you can do is solve a similar problem like with the stub matching. So you go on the Smith chart, which is here. Copy. Paste. And then let's clean it a little bit. Okay, now what you can do, I want to make it bigger. Okay, so now you need to find where your load is. Your load normalizes 2 minus j 0.6. 2 is here, the real part. 2 is here. And then minus j 0.6, 0.6 minus j is there. So the intersection of these two gives you ZL normalized. And then you have to go to the center of the chart. So how do you do that? You have to find the circle that goes around here. All right, and then from here, you will have to get to the center of the chart, which means that you will go here and then move here. And this is something that if you go to your notes, is something that we have done in 322. All right, it's fundamental to transmission lines, to Smith chart. So that is the solution. It's the way to solve this problem. However, when you go down to other problems, you want to start taking the design of problem 2 and then realize it in microstrip. So you will have, after you do the design on the Smith chart, all right, after that, you will have to take the values from here, which are in wavelength, and then Z naught, and use the formulas in the section of the chapter to find the width of the microstrip and the length. All right, so in find the wavelength, obviously, and the length. And then it says the frequency is 2 gigahertz. All right, and then the last one is a continuation of problem 3. So the problems that I have given you are much easier than the problems I solved here. But I did that so you can see how we are thinking in design. All right, it's not only just to solve the problem for the homework, but is to see exactly how we are working for a particular design. So do you have any questions for me in addition to everything that I covered? Any questions? I don't hear. So are you satisfied with the comments I've made?
Yes, thank you. Thank you so much, Professor. That was helpful.
Okay. All right, perfect. Okay, so if you have any additional questions on Saturday. All right. Okay.
Thank you, Professor.
Yeah, thank you.